Hi everyone. So I'm going to give you a talk on a little bit of what my PhD entailed in the first and a half year. If you were at DDL, you might find it familiar. It's because you've had the pleasure or possibly the pain of sitting through it. But yeah, here we go. Does this work? Oh, it does. Perfect. So yeah, just a quick background. You've probably seen or even used nasal spray pumps that look something like on the screen right now. And they're usually used to deliver drugs quite locally in the nasal cavity. However, more recently, people like myself are interested in seeing how well these devices work on delivering drugs systemically and also to the brain. What's interesting with these devices is that they rely on shear rate that is generated during actuation to actually break up liquid bulk into finer droplets, and that's through the process of primary and secondary breakup, which you should remember from CAS, hopefully. What we assume is that, generally speaking, these nasal devices generate a shear rate in the in the range of 10 to the 5 reciprocal seconds. So what's the problem, you're thinking to yourself? The problem is that when you use high viscosity formulation, that shear rate generated drops quite significantly, because shear rate is actually a function of velocity, which in turn is a function of this viscosity of your formulation. So in the same geometry, depending on your formulation's viscosity, you're going to have different shear rates generated. Therefore, we're actually limited on the amount of mucoadhesive viscosity modifiers that we can use in nasal formulations. And because of that, we have limited retention time in the nasal cavity. So what's the motivation behind this work then? Newer devices, for example, Bestbac's Nasodose, is using a more optimized flow path and actuation mechanism. And as a result, we suspect that it's able to generate shear rates much higher than we previously expected. Because of that, we again suspect that we should be able to spray formulations that are a lot more viscous than previously thought to be possible. So the aims of our work, we aim to generate a computational fluid dynamic model that's able to do three things. Firstly, study the flow of Newtonian and non-Newtonian formulations in a Nasodose device. Secondly, understand the shear rates generated through non-Newtonian and Newtonian fluids in a Nasodose device. And finally, the favorable rheological properties for sprayability in the Nasodose device. So what did we actually do? First thing we did was study the rheology. This was important. We had to understand the viscosity of the formulation we want to test. For example, the formulation we used here is polyethylene glycol 4000 at concentration of 50%. And we studied the viscosity at shear rates ranging from 0.01 reciprocal seconds to 10 reciprocal seconds using a rotational rheometer. Moving on to the geometry and boundary conditions. So these are quite important for CFD models because that's where your simulation takes place. And you can see that we've actually generated a CAD, a computational aided design, where you've got the wile system here leading to a needle, a swirl chamber over there, and also the nozzle there where the fluid exits from. So this was actually the internal drug pathway in the Nasodose device. And in terms of the boundary condition, we have an inlet velocity on the left-hand side, it would be, and everything else is a non-slip wall connected to the pressure outlet at the nozzle on the other side. Physical models, very important in CFD, and if you want to talk about this in a lot more detail, I can talk to you about this for a day, but just to keep it short, I've talked about the two main ones I've used. Volume of fluid is the most important. What this is a Eulerian multiphase model, which allows us to locate and track the liquid-air interface. As you can see in the images I've professionally stolen from Wikipedia, it's very nice in sort of tracking that liquid-air interface. You can see very easily, you've got a drop there, but as soon as it contacts the water there, it starts splashing, and it's very good at kind of tracking that, which is what we want in a nasal device to understand the fluid flow. And secondly, the K omega shear stress transport. So this is a turbulence model. It allows us to understand the flow within the device So at the needle, our flow is quite transitional, whereas at the soil chamber is quite turbulent. So K omega shear stress transport is quite good for that mixed turbulence model. Moving on to the results. So rheology, like I said, this is quite well known, but they et al. Did a very good job here. They've identified that actually sprayability and the formulation viscosity that you can spray is very dependent on the nasal pump that you use. For example, in a traditional nasal spray pump, you were only able to spray a formulation that's about 4 times more viscous than water. Whereas in a high viscosity pump, you're able to spray something that is approximately 20 times more viscous than water. What we then did was really just try to one-up them. So our formulation at 0 shear is about 300 times more viscous than water. You can see that there is a shear thinning region over here where the viscosity drops as the shear rate increases. And finally, we got an infinite shear zone there where there's a plateau at about 0.03 Pascal seconds. That's about 30 times more viscous than water. You're probably thinking to yourself how we added this to the CFD model, and that was done using 2 equations. So the power law model, which looks at the green line on the graph, and that's kind of the shear thinning properties of the formulation, and the cross model, which looks at the infinite shear and the 0 shear viscosities that I mentioned to you previously. We inputted that into the CFD using some simple codes and ran the simulation, got these results. So water and polyethylene glycol fluid flow in the needle looks very similar. If you had the ability to zoom in, you can see that the polyethylene glycol formulation flows slightly more parabolic, and that's because the more viscosity being given a lower Reynolds number, so the flow is slightly more parabolic compared to water, but honestly, they're pretty much the same. Moving on to the interesting part, it's actually the fluid flow in the nozzle and the soil chamber. So what we can see here is that both formulations are able to generate an air core. Think of an air core as a hurricane. In the center, you've got the eye of the storm where the pressure is the lowest, and as a result, the air gets sucked into that region, and all the fluid remains around the sides of the soil chamber. There's quite a high vorticity there, and as a result, the velocity increases as it gets closer and closer to the nozzle, and that gives the energy to actually for the liquid bulk to break into fine droplets, and you get spray generation. So presence of that air core is very important for these formulations to spray. The differences between the two is that with the water formulation, you can see very easily where the air core is. It sort of starts at the base of the soil chamber and carries on to the nozzle, compared to polyethylene glycol, where the soil chamber is very much at the top of the nozzle. So we can actually see that the device, although it's able to spray this formulation, it's reaching its limit with viscosity. Moving on to velocity, similar thing again. So we can see that the velocity at the liquid air interface and where the liquid bulk is around the edges of the soil chamber is highest. That's where we have the energy to cause that breakup through the primary and secondary breakup and atomize the formulation. You can also see it with polyethylene glycol, not so much around the inside, like kind of mid soil chamber, but near the top where the nozzle is, you can still see that the velocity is quite high, so we have enough energy for atomization. What's interesting is if you can't really see it here because of the tab underneath, but over here at the base of the soil chamber here, we can actually see that the device is really trying its best to generate that soil chamber. So you've got a small region of high velocity, but it's just struggling. There's just not enough force in it to be able to do so. Strain rates, quite similar to velocity, so I'm going to go through this quickly. We can see that the strain rates are highest at the liquid air interface, but more interestingly, what I want to talk about is the shear rates that we see over here. So the shear rates at the liquid air interface for polyethylene glycol are approximately 1.5 to the 6. If you remember in the first slide, I told you in traditional nasal spray pumps, we were only able to get shear rates in the region of 10 to the 5 reciprocal seconds. So we are using a formulation that's a lot more viscous than traditionally used, and we're getting a shear rate that's an order of magnitude greater than what's expected, which is exactly why we are actually able to spray these viscous formulations in our devices. So what does all this mean in clinical use? I've given you loads of simulations and assumptions. You can see here that we have from the left water, medium viscosity silicone oil, which is approximately 20 times more viscous than water. It's kind of cut off because of the tab underneath. And high viscosity emulsion, which is 900 times more viscous than water. And we can see that all of these formulations are actually sprayable. This is mind-boggling. The high viscosity emulsion should not be sprayable in a nasal spray pump, but obviously with the NasoDose device, we're generating such high shear rates that it is becoming quite possible. So conclusion, NasoDose is able to generate high enough shear rates and velocity to generate sprays with viscous and non-viscous formulations. And secondly, the CFD model developed allows us to do two very important things and quite rapidly. It allows us to estimate the sprayability of various different formulations with various viscosities using the same device. But also, if you are interested in one specific formulation, it also allows us to actually look at how we can fine-tune the device by changing the diameter of the nozzle or the actuation force to actually understand how we can fine-tune the device for sprayability of a specific formulation. So it gives us both of the benefits of that. So it would be quite hard to actually physically change a device. In practice, you need to go back to the drawing board, but in CFD, you can just change a number and it changes everything for you. I'm reaching the end here. So acknowledgements, Dara Manane and my research group at University of Hertfordshire, Michael Cook and my research group at University College London, Adam and Sabrina from BestSpac, and just a few more, so EPSRC, UHHBC, and the CDT. Thank you very much. I'll be happy to take any questions.
Thank you, Hessam. Do we have any questions, Hessam? Two over here, so we'll go one at the front first. Rachel's just. Oh, we're going to go.
Could you tell me a little bit about the boundary condition for your comparison? Was it a flow rate for the two, or were we using the same actuated pressure?
So we use the same inlet velocity for both the formulations, so that it was a constant velocity at the inlet, which was set at 0.131 meters per second.
And did you calculate the force? Was it realistic for the high viscosity stuff?
For the low viscosity, it is. For the high viscosity, it is a bit of a stretch. However, the benefit of using the NasoDose is actually we use a spring actuated device, so it's not actuated by a person as such. A person just needs to have enough force to be able to actuate the device. The spring does the rest. For example, at the moment, NasoDose uses about 20 newtons of force within the spring, and that can easily be changed depending on the requirement needed.
Thank you.
Thanks.
Rachel, there's one here.
I'm just curious about how you validated your model there. It's a very small environment.
So the model is not validated completely. It is very difficult to validate, like you said, because it is sort of a microfluidic issue. It's very difficult to actually estimate the velocity of everything within the system. However, what we have done is we have validated the inlet velocity using the spray view device. So what we've done is we've used a force that is able to move the plunger down. I don't know if you've seen how nasal sprays, the unit dose nasal sprays works, but there is a plunger where that plunger is moved down into the vial and that pushes the liquid up. And the velocity at which that plunger moves down is the velocity at which the formulation enters the needle. So that's how we've decided what inlet velocity to use. However, the simulation isn't fully validated. What we are trying to do is validate it using SprayTech data later, but that would just be how long it takes for the spray generation for the spray to leave the nozzle. It would be very difficult to actually validate the kind of the internal flow mechanisms.
And Rachel, there's one over here, Adam.
That's really interesting. You mentioned being shear heavy, which is quite interesting. So a couple of questions. Yours vary by viscosity emulsion. Is that viscosity at zero shear, or is that even?
So I don't have the answer to that because that's something that we've done previously. It's not part of my specific work. However, what I can say is that it is a shear thinning formulation, that one. Also, it is a thermal responsive formulation as well. So the viscosity increases as the temperature gets closer to the nasal cavity's temperature. That's another aspect of my PhD, which I didn't have time to speak about, but we are looking at thermal responsive gels as well.
Is the shear thinning incorporated into your model? Like, did you get specific bits of behaviour that only happen because it's shear thinning that wouldn't happen for any general fluid when the high rates?
So realistically, the shear rates are so high in the simulation that almost immediately after you start the simulation, it becomes the infinite shear viscosity. So realistically, you could actually just use the infinite shear viscosity for the simulation, but we've already coded for the simulation, so we thought we might as well include it. But you could potentially just ignore that zero shear viscosity because as soon as you start the simulation, it becomes infinite. Yeah.
Okay, thank you very much, Hessam.